Hello everyone, my name is Piotr Dyszewski and welcome to my video about branching random walks, stretch exponential tails and Gumbel distribution. So in this video I wanted to say a few words about a joint project with Nina Gantert and Thomas Hüffelsauer from the Technical University of Munich. So let's start with the description of the model. So we will work on the real line, and at time 0 we place one particle at the origin, and at time 1 a couple of things happen. So first off, this particle dies and gives birth to a random number of new particles, and we're going to assume that the particles reproduce according to a Galton-Watson process, with reproduction mean strictly greater than 1. So secondly, these particles are placed somewhere on the real line, and we're going to assume that the displacement of a particle from the place of birth is an independent copy of a given random variable, say x. So now the dead particles are removed from the system, and whatever remains evolves in the exact same fashion, independently from other particles. So they die, reproduce, and their offspring is placed somewhere on the line, and we continue in this fashion. After some time, we see a collection of particles on the line, and we want to understand how this collection evolves. So, for example, we can ask about the rightmost particle, right? And this Mn is going to be exactly the random variable that I'm interested in during this talk. Branching random walks have been around since the 70s, and obviously a lot of things are already known. So let's put everything into perspective. So whenever I write P star, this is going to denote the conditional probability given the non-extinction of the corresponding Galton-Watson process. So in the classical case, when the displacements have light tails, it has been shown after a series of works that after a linear and logarithmic correction, you see a limit in distribution, and this limit can be expressed as a random shift of a Gumbel law. Here the shifting random variable d is a limit of so-called derivative martingale associated to the branching random walk. So on the other side of the spectrum, we have tails that are very heavy. I mean that they decay like t to the minus beta, and by this twiddle I mean that the quotient of the left and of the right hand side tend to 1 as t tends to infinity. So it has been shown in the early 80s that after appropriate scaling we again see a random shift, but this time we are shifting the Fréchet law, and the shifting random variable is a little bit different. I'm going to talk about this W in a minute. So when you look at the proofs of these two theorems, you will notice that phenomena that cause these two behaviors are extremely different. So this is quite natural to consider tails that are in between, and this is where the stretch exponential tails come into play. So I'm going to assume that the probability that x is greater than t decays as e to the minus t to the power r, and the shape parameter r is somewhere in between 0 and 1. And what I want to advertise today, and what is our main result, is that after an appropriate polynomial correction and polynomial scaling, we again see a random shift of the Gumbel law, but this time this shifting random variable is the same as in the regular variant case. Alright, so one thing needs to be said, that is this first term asymptotic expansion was actually established previously by Nina in the 2000s, and our main contribution consists of delivering the corresponding limit theorem. Alright, so to understand what is going on, we need an appropriate graphical representation of the branching random walk. So take your Galton-Watson tree and label the vertices however you like. Then take ID copies of x, of the displacements, and treat them as labels of the edges. So now, label of each edge represents the displacements of a given particle from the place of birth. So, if you are interested in a position of a particle from generation n, you have to take the path from this particle to the root and sum all the edge weights along this path. And this exactly represents the position of this particle. Alright, and with this notation, Mn is exactly the maximum of these guys. Alright, so now, since we are assuming that our tails are sufficiently heavy, we're gonna use the corresponding big jump principle. And the easiest way to phrase that is that, well, if you take two ID copies of x, the probability that the sum is big is asymptotically equivalent to probability that one of them is big. And in principle, what we want to do is to see how this principle works on trees. So naturally, we want to look at the maxima first, because it's easier. So take the biggest displacement of each particle up to time n and start by writing a limit theorem for this guy. And this is really easy because the displacements are IID and they are independent from the branching mechanism. So by simple condition on the tree, you see that after polynomial correction and scaling, you see the exact limit that we get in our in our theorem. And here W is a martingale limit associated to the underlying Galton-Watson process. So as I said, the proof is quite straightforward. So if you are interested in the details, and if you are interested in the values of each of the constants, please pause the video right now and read the proof in detail. And otherwise, we'll just continue. All right. So we know that the first order asymptotic expansion of the rightmost particle coincides with the first order asymptotic expansion of the biggest displacement. So in order to understand the rightmost particle in detail, we need to first look at the biggest displacement. So draw your Galton-Watson tree up to level n, and now look for the displacements that are roughly of the correct order and color them in green. And then look at all the paths that pass through those edges. So there are some branches that are below those guys, paint them in red, and then the branches that are before, they are going to be painted in orange and blue. And the way those two last color work is that when you look at different big jumps, a part of the segment is going to be disjoint, right? And after some time, they're going to intersect. So the orange part is just the disjoint part, and blue part is just the common part. All right, so you can easily convince yourself that those particles that are not, colored do not contribute asymptotically. So you can only look at the colored particles, and position of each such particle can be decomposed into 4 terms according to the colors. And now you need to look at the maxima a little bit closer. First of all, you don't see too many maxima, and since the maxima are uniform on the tree, when you take 2 big jumps, they're going to be very far from each other on the tree distance. So this means that this blue part is going to be negligible asymptotically. So this is one thing, and the second thing is that when you look at when the big jump happens, by the number of particles, basically, it has to happen very close to the leaves. This means that those red parts are going to be small, and this in turn tells us that asymptotically this red term is negligible. And we are in business, because now asymptotically what matters are those green big jumps and those long orange segments, and those are independent. So we look at that and we know what is the asymptotic behavior of the big jumps, right? And then we look at the contribution of the typical particles, and we see that they're going to contribute by this deterministic polynomial correction. Right, so this is way easier said than done, and on the technical level, this corresponds to understanding precise large deviations for sums of IID random variables with stretch exponential tails, but this has been done in the late 60s. So if you put everything together, you see the following results. So if you assume that your displacements are centered and you have unit variance and have stretch exponential tails, then under some technical assumptions that include, for example, the Keston-Stigum condition, you have a limit law for the rightmost particle. That is, there are constants gamma, sigma, and beta j, such that if R is small, then the limit theorem is almost exactly the same as for the biggest displacement. And if R is bigger than 2/3, then you see the contribution coming from the typical particles. You see the contribution coming from this orange part, and the closer R gets to 1, this contribution gets bigger and bigger. And yeah, if you look at the formula, you just notice that whenever R is of the form k over k plus 1, you see a transition in the behavior. I mean, you will see another term popping up in the limit theorem. All right, and that's that. So this approach, in my opinion, is quite robust and did allow us to treat, for example, large deviations for this model, and also treat the corresponding point process convergence. And the last one, it's still under preparation, but it should be available online somewhere towards the end of the year.